Hi everyone, welcome to the seminar. I'll probably give it another couple of minutes just to give people a chance to turn up, I guess, and then maybe get started about 3 past, if that's okay with everyone. So now feels as good a time as any to get started. So thank you all for coming to this slightly strange, Ben just messaged to say he might introduce me, so that might be a better way of doing things. So Ben, do you want to take it away?
Cool. Thanks, Andrew. No worries. Really happy to introduce Andrew. He's a postdoc in the school who's been working in the defense area with, first he was in electrical engineering and now he's in computing information systems as a postdoc in adversarial machine learning. He received his PhD in applied and computational maths from Monash in 2018, where he was working on a class of algorithms for solving nonlinear variable coefficient differential equations, quite a mouthful, with applications to fluid mechanics. He's been working in machine learning recently. He's interested in robust neural network design, large-scale computational game theory, graph neural networks as well for temporal patterns. So over to you, Andrew.
Cheers, Ben. So today I'm going to be taking everybody through a little bit of an introduction to robustness in an adversarial machine learning context. And this work is based upon work with my collaborators, Ben, obviously, who just introduced me, but also Sarah and Shiji from the School of CIS at Uni of Melbourne as well, and Paul Montague, who's from DST in Adelaide. There we go, I can actually change the slide, that's useful. So in a little bit of context, deep learning has obviously been shown to be particularly powerful in a whole bunch of academic data sets. And now that promise is starting to be translated into commercial and industrial applications as well. So we're now moving into the realm of seeing things like fraud detection in finance, chatbots, vehicle navigation, visual parsing, and voice recognition, all being applications of deep learning in an industrial context. And the reason for this is because the deep learning performs particularly well in all these contexts. These are generally spaces where there's large data sets. The data sets have large numbers of dimensions that are very difficult to kind of parse and algorithmically approach using non-deep methods. Whereas deep learning methods are able to really synthesize a functional relationship between whatever our input set is and whatever our output set is. And so this has been used, like one example of this is that Taylor Swift used facial recognition software to detect stalkers. This is an example of where Taylor Swift concerts would obviously have hundreds and hundreds and hundreds of thousands of people across a concert series going through her events. This is a large data set of people whose kind of images would need to be parsed and compared with a small set of potential stalkers. And this has been a successful application of deep learning. The problem with deep learning, though, is that the results that we report when we talk about deep learning are always based upon an assumption about the set that the inputs to the model will be tested against. And when we start moving to out of distribution samples or to crafted distribution samples, we can really start to mess with the performance of deep learning systems. And that's where adversarial behaviors really start to become important. This is basically another way of thinking about this is the realm of spaces where deep learning goes wrong. So in terms of adversarial learning, one of the things that we're really interested in are changes that would be imperceptible to a human, but would produce a completely different or a complete change in the model's behavior. So this might be changing the classification results of the system, or it might be changing a prediction, a classification, anything like that. Or it could be not being able to even make a prediction at all. And the importance of considering these things is that when we start to deal with deployed systems, especially on an industrial scale, there's often incentives to manipulating the model behavior. These incentives could be financial. So if we've got a fraud detection system, being able to make a small change to, say, a loan application that a human wouldn't flag as being any different, but that an AI system might treat as giving a completely different output. We could be looking at privacy-preserving incentives, or could even having malicious incentives. So one example that's quite commonly seen in kind of the adversarial space is changing the results of facial recognition systems. So on the right here, the two images at the top are people who've had carefully crafted glasses essentially superimposed on top of their faces. Now, you would say that these people do not look anything like Brad Pitt, but with the addition of these glasses, the person on the right is classified as Brad Pitt, and the person on the left is classified as this person whose name I can't remember off the top of my head. So a very small crafted change is able to trick a facial recognition system into picking a completely different person. Obviously, in the context of the Taylor Swift stalker detection, if you're able to just put on a pair of sunglasses that allow you to evade a stalker detection system, kind of defeats the whole point of having the stalker detection system in the first place. This is less an attack, but more a concern with machine learning, is that where sometimes there's the risk of de-anonymization occurring through manipulating the model itself, and so causing the model to release behavior. Obviously, this is a bit of a stretch based upon the example I've given, but this is some work that Ben did that was really interesting on de-anonymizing Mikey work a year or two ago, Mikey releases a year or two ago. Probably this again is less a classical example of an adversarial attack, but also an interesting example of what can happen to deployed systems when we put them in the wild, is that a few years ago, Microsoft released a chatbot named Tay, and they put it out on Twitter and allowed Tay to learn from its interactions with people on Twitter. And for anybody who's been on Twitter before, there's probably an inevitable conclusion here. And that's what ended up happening, is that Microsoft's chatbot became a racist, drug-smoking, horrible person, basically, as a chatbot. So obviously this posed a reputational issue for Microsoft, but it's also an example of just what can happen when you deploy a system that's based upon deep learning and don't necessarily think about how that system is going to behave in the case of adversarial examples and what the incentives are for people to mess with the model behavior, essentially. Final example I've got of kind of things that aren't quite adversarial examples, but kind of ways that we can think about adversarial behavior, is an artist by the name of Simon Wecker, who's based out of Berlin. And he noticed a couple of years ago that he saw basically a strange behavior in Google Maps in terms of how it was showing traffic jams. And he decided to see if he could attack, essentially, Google Maps' algorithms for detecting traffic jams, which are based upon the speed of phones moving through an area, and to see if he'd be able to trick it into inducing a traffic jam on an empty bridge. And so he put 99 phones in a little trolley, had SIM cards in all of them, had Google Maps running, and just walked slowly up and down the bridge. And this was enough to induce Google Maps to say there was an incredibly bad traffic jam on that bridge, and to change Google Maps behaviors so it routed everybody. Well, everybody suggested routing routes were to avoid this bridge. So again, this is not necessarily what we classically think of as being an adversarial attack, but as an example again of how incentives on deployed models can really produce some interesting results, and why we need to think about adversarial attacks when we think about both deployed models and also in terms of academic research as well. So for a more formal definition, in an image-based context, the most basic kind of adversarial attack is that if we have some input X returning that one class I has a higher probability than all the other classes, or a higher value on our outputs in our classifier. An attack sample might be to add some perturbation V to that, so that class I is no longer the largest reported class. This is a kind of a generalized label flipping attack, which seeks to simply just corrupts the model's behavior for one given sample X. And in general, what we're looking for is we're looking for perturbations V that are very small. And so often what we do is we kind of constrain them to be of a certain size or a norm bounded size. And we go, okay, is it possible to construct one of these? So to give some kind of more visual examples, if we, starting off with the images, we have on the left a duck. It's a duck with some other behavior in the image, but we should be able to train a system to detect that that is a duck. Now, if we add some randomized noise, which is then scaled by a very small amount, we end up with an image that to a human looks exactly the same as the duck. No human is going to misclassify that. If anybody who's able to recognize the first image as a duck is going to recognize the second image as a duck as well. But in this case, the classifier returns the value of returns a prediction of a horse, which is obviously completely incorrect. In terms of a voice print, because we're not just limited to visual systems, we can also have it in acoustic systems or really any deployed ML system. We could start off with a voice print saying, "How are you?" adding some random noise, and this might be changed to "open the door." Now, this is a particularly interesting example because say you're trying to design a secure system where somebody has to use their voice prints to say a non-predetermined message. So as in they're given a prompt, they have to respond to that prompt in some way. That is the key to unlocking a system or something like that. Now, ideally, that system should be based just upon the person's voice print. But if the system has the potential to be adversarially attacked, it may be that just a recording and then adding the right noise would be enough to switch what the system is hearing, in inverted commas, and potentially allow this system to be unlocked. Now, the reason why these adversarial attacks exist is that essentially we're feeding machine learning systems training and test data that is discrete and is a subset of kind of the overall space. And then our models are trying to build a continuous representation of that space that fits to all the training data. And while that at the training data points, generally we end up with good, strong classification performance, we don't have any great kind of ability to see how close classes are at a single point. So for an example here is if at this point X is returning the blue classification, but it would only take a very small perturbation to move it into the green region. And this is kind of what we think of as being having the potential for an adversarial attack, that it would be very simple to add just a small amount of crafted noise or crafted perturbation to our point X to move it into the green region and change the performance of our classifier from reporting blue to reporting green. And it's this sensitivity to perturbations and the ability to really change the results of a model with very small, imperceptible changes that really makes it important to kind of think about the fact that when we look at a model, we're generally looking at like its accuracy, its top 1 or top 5 accuracy. But those headline figures can disguise the fact that there can be a significant drop off of accuracy as we move away from the distribution of data in our test set. So for an example of this, with an Inception V3 dataset, an interception v3 model trained on ImageNet with the basic kind of standard test set. The top one accuracy is about 0.76. But as we add 2 norm noise to that, that headline accuracy drops off incredibly quickly. To the point where if we're adding 2 norm noise with a norm size of 1, the accuracy drops off to essentially 0 top one accuracy, which is a kind of an alarming factor when you think about these things in terms of, oh, well, it's a 76% accurate model, but it's only really 76% accurate to our test set. And it's very easy to move away from that test set in such a fashion that it would completely destroy the accuracy. An example of where this might occur in practice is that if we had all our images taken with a very high quality camera for our ImageNet dataset, and then we deployed the system based upon a webcam, that might be enough of a corruption of the types of the visual data that we're seeing to significantly degrade the top one accuracy. And it turns out there's actually a balance in models between their accuracy and their robustness. So on the horizontal scale here, we have top one accuracy. And on the vertical scale, we have a measure of the resistance to robustness. It's not a particularly standard measure, but it's such a great graph, such a great figure that I kind of couldn't go past it. And so what we find is there's essentially a Pareto front, the red line, that describes the relationship between, well, the trade-off between accuracy and resistance to, and accuracy and robustness, essentially, for models of sizes given by the size of the circle, essentially. And so what we can see is that models like Inception produce high top one accuracy, but they're very sensitive to perturbations. Whereas a model like AlexNet might have a lower top one accuracy, but is much less sensitive to the addition of noise and is theoretically going to be more robust. Obviously, there's also mobile nets, which kind of just sit in the middle. But for kind of models that are treated seriously due to their size, there's this kind of, there seems to be this fairly fundamental trade-off. Now, when we're talking about robustness, I've so far mentioned just adding noise or crafting noise or stuff like that. The way this is performed is by constructing what's known as an adversarial attack, which is where we try and minimize the size of the noise that we're adding that is enough to induce a label flipping change or to induce some other sort of adversarial behavior. So we might want to just corrupt the output or in some fashion. Now, there are a bunch of different attacks in the literature. Fast gradient sign method is a particularly common one. Cullen and Wagner is another known attack that has been performed quite well. However, in general, essentially, as you probably should be able to guess from just the formulation of this minimization problem, all these attacks essentially can just be generalized as variance of gradient descent or projected gradient descent. And so we're using projected gradient descent to try and find the level of noise which is enough to flip the label either to a random class or to another specific class. Now, of course, since there has been research into these attacks, that's obviously motivated people to try and develop defenses to these attacks as well. And these defenses, or known as adversarial defenses, have been rather successful. They can either prevent an attack from being able to work, or at least increase the difficulty of the attack in how much noise is required to be added, or how much computational cost is required to construct an adversarial example for any particular test problem. The problem with these defenses, though, is that defenses are generally not general, in that a defense is specific to a particular attack. So there's this attacker-defend attack paradigm, where an attacker's propose a new method, and then the defenders come in and say, okay, we can stop this particular method by making this modification to the model. And crucially, these are generally model modifications, so they generally require retraining. But they're not, because they're not general, a defense is only as good as the current, as the attack is only good against the attacks that it's been designed against. And so as such, if somebody comes up with a new attack, a defense may not hold against it, or at least is not going to provide any guaranteed solution to any new attack. So because of this kind of attacker-defender paradigm and the kind of the need for defenses to respond to particular attacks has motivated a new branch of research known as certified robustness. Certified robustness is where we try and provide a guarantee that no perturbations exist up to a size given by the guarantee that will be able to change the behavior of the model for a particular test point sample. So the nomenclature here is that we're looking again for perturbations V, and these perturbations are inside some ball, p-norm sized ball of size L, and that for all perturbations inside that ball, we preserve basically our output class. And if we're able to do that, if we're able to provide that guarantee, this is a certified guarantee, and we basically can say, okay, this test point has a certified robustness up to size L. Now, there's two main mechanisms that have been used for providing these kind of certifications. The first type are noise-based mechanisms, in which noise is added to the model or to the weights or to the input data. Missing that point in the slide. In order to try and basically smooth out the output of the model. And by smoothing out the output of the model, the aim is to try and minimize the existence of small regions which would admit an adversarial perturbation. This second approach are known as Polytope Bounding mechanisms, where basically a bounding polytope of the output is derived through back propagation. And this is able to then kind of give a bound as to where the model output can move to based upon an input perturbation. And we'll see a little bit more detail of that in a minute or two. So of the noise-based mechanisms, these were kind of initially came from a work by an author by the name of Wecker, who I haven't cited here, but who used a mechanism known as differential privacy to prove that, to prove robustness of samples. So differential privacy as a technique is based upon looking at a database, which in this case is represented by all our images up at the top. And we pass that database through some magical mechanism and it produces an output. And then differential privacy is saying, okay, if we make one change in that record, so now we move to the bottom row where we've deleted one entry from our record. If we pass that new database through that same magical mechanism, we should get an output that's basically the same. And so this is the idea of differential privacy. And obviously this should be kind of there should be a clear kind of connection here between this and with robustness. Because with robustness, we want to say that, okay, for any small change in our input point, if we can pass it through some mechanism that makes it imperceptible, like that change to be imperceptible, then we've essentially provided a guarantee of robustness. We've been able to show that there's no adversarial example can exist. So in a little bit more detail, differential privacy can be mathematically stated as this equation up the top here, which is that there's a bounding relationship between the output of a model A when it's exposed to some data set D, and when that model A is exposed to some data set D prime for any possible D and D prime. Now, these are obviously databases, but it can be generalized to test points as well, and to change it to being a norm-bounded perturbation between the two samples. And what we can end up with is a maximization problem, which defines the largest possible ball, where the ball is of size L. So this is a P norm-bounded ball, where this size is kind of bounded by these criteria in here. Now, one thing to note is that differential privacy is expressed in terms of probabilities, but our robustness measure is in terms of expectations. Now, the transform from probabilities to expectations is necessary in machine learning because we can't access the direct probabilities of a model's output. but we can sample the expectations by adding noise and then consistently passing that noise through the model again and again and again and again and again, and allows us to build up a Monte Carlo expectation. And then this basically becomes the output of our sample point X. So it's this process of adding noise, which is our magical mechanism here. And if we carefully construct the noise, we're then able to balance the nature of that noise, in this case through the standard deviation of the noise sigma, with a whole bunch of other parameters which aren't really important for the moment here, to end up being able to get a test time measure of a sample's robustness, or how large a size of perturbation we can guarantee does not induce changes in the output of the model. Now, there are other noise-based mechanisms as well. Wecker, who originated this idea of using differential privacy to construct robust samples, proposed a method in 2018, which was quickly followed by Lee, also in 2018, who used Regnier divergence to come up with a tighter bound on the size of the guarantee that could be provided, which essentially meant they were able to increase the size of the guarantee. And then Cullen, who used essentially the structural worst case behavior of a model to come up with a representation of the relationship between the expectations of the model, or the expectations of the largest class, and the size of the guarantee that can be provided. And so what we end up with from these four techniques is that there are different ways of describing the expectation, describing the radius of certification for a given technique. And importantly though, no one technique actually dominates any of the others. The performance of each of these techniques depends upon the outputs of our model and kind of the distribution of the outputs of our model. So as an example of this, I've put in here some results from a paper of ours that's currently under review, which looks at the certified accuracy against radius for ImageNet data trained on a ResNet. And so if we look at, and what we're looking at here is the vertical axis is a certified accuracy. The certified accuracy is the proportion of samples that are classified correctly with a radius greater than the radius in the horizontal axis here. And so what we find is that our technique and Lee's technique both start off performing fairly well. They produce a certified top one accuracy of about 0.55, which is pretty much as good as you can kind of get at the moment for ImageNet data. But their performance drops off fairly rapidly. There's a upper limit on the radius certification provided. Whereas Cullen's technique does not perform as well on the initial top one accuracy, but as it does provide certifications with a much larger radius for a subset of samples. The reason for this is that there's an analytic relationship between the class probabilities and which technique is going to perform best. And so this analytic relationship is in the second figure on the right here. I'll just quickly walk you through that. So this figure is plotting the relative radius between the certification technique that we've currently proposed based upon differential privacy and the best certification of Lee's technique, Cullen's technique, and Wecker's technique. And what we find is that as the highest expectation goes to 1, our technique underperforms relative to both Cullen's and Lee's techniques. But as the output becomes more contested, so when our highest class expectation is closer to our second highest class expectation, our technique begins to outperform the other techniques and is able to show improved radius of certifications. And so this is an important kind of understanding when it comes to certifying things, is that it's not just the model that influences the robustness of a particular sample point, but also it's not just the model and the certification technique, but it's also the actual sample point itself can change the relative performance of different sample techniques because of how close the classes are together, essentially. Now, as I mentioned before, there's a second approach for constructing certification. So there are the noise-based mechanisms of the previous slides, and there's also deterministic approaches using polytope bounding mechanisms. These techniques look at the range of possible outputs for each layer of a neural network based upon its weights and its shape, and use this through backpropagation to start building up a picture of what the bounds of a model can look like. So in the upper image here, we have just a simple ReLU layer, and we can say using for perturbations up to size, let's say this is about 1.5, so this gray region here, between -1.5 and 1.5, we can, by different techniques, we can say that the output is either bounded by the red line or the blue lines. And so these are based upon IBP, which is one kind of bound propagation, and linear bounding, which is another type of mechanism. And so these approaches look at not just one single layer or one single neuron in a network, but the whole network altogether. And so they look at the input and its initial and its allowable perturbations, and then they propagate those allowable perturbations through the deep network and end up with a final layer kind of adversarial polytope, which is the bounding region in which any output, any adversarial example could end up in. And so this can then tell us if it is possible to construct an adversarial example for a given model. Now, this technique obviously provides you with well, you may be able to guess that this technique provides you a stronger kind of guarantee, a stronger kind of amount of knowledge, because we are getting this bounding polytope, we are getting a shape, not just a value of how large the largest perturbation we can guarantee doesn't change the model. But when we compare these kind of two approaches, these deterministic polytope-based approaches and the noise-based mechanisms, the advantage of the noise-based mechanisms is they can essentially be applied to a black box model. All you have to do to apply a noise-based mechanism successfully is to be able to train with noisy perturbations. You don't have to have any access to the internal mechanisms of the model, and you can train using your standard loss functions. There's no engineering that's required, essentially. Whereas the polytope methods generally require a very specific training methodology. They require you to change your output functions and your loss functions. And the training costs for these can be more significant, especially when you start having to propagate the bounds through really deep neural networks with millions or tens of millions of parameters. So there's definitely a trade-off between the amount of information we can get out and the complexity of implementation, complexity of engineering. Now, finally, I'm just going to, when it comes to test time samples, I'm going to, one thing that's kind of become clear in our work at looking at test time certification is there's really a significant overhead in terms of the difference between the size of the guarantee that you can provide and where the nearest adversarial perturbation actually is. So that we can only provide guarantees up to a fairly small radius, but the nearest adversarial guarantee, the nearest adversarial point might be significantly further away than our guarantees. So basically there's significant ground for improving the size of our guarantees. If we can improve the computational techniques, hopefully we can improve the size of our guarantees. And if we improve the size of our guarantees, hopefully they're more useful, they're more relevant. We can tell more about the model's behavior. And so on the right here, this is just a basic CFAR10 model trained with a small ResNet. And we have some of the techniques I've been talking about before for noise-based mechanisms. And then in the red line, we've got a new noise-based mechanism that we're still kind of ironing out the kinks of, essentially. But it looks like there's promise here in trying to really significantly increase the size of the radius of certification for test time sampling using noise-based mechanisms. And so this is something we're really excited to kind of keep on working on, because if we're able to increase the size of the radius of certification, we're really able to give much stronger guarantees about model behavior. Now, everything I've talked about up until this point has been on testing time adversarial attacks, where we change a test data point in some way to try and flip the behavior of the model. But another kind of adversarial attack are what are known as training time attacks, where the data set of the model that the model is trained under is corrupted in some way to change the output behavior of the model. Now, this change could be simply just to corrupt the model so that it performs much worse than you would otherwise expect by the addition of these adversarial examples. Or it could be to try and sneak in a backdoor into the model where a subset of the data set that it might be exposed to reports differently than what we would expect. And so again, this is the kind of thing that might have security implications, or it might have just issues with robustness or privacy or any of the other kind of major concerns we should be thinking about when we're looking at deployed systems. Now, when it comes to training time attacks, one method for looking at training time attacks is essentially to partition the data set into random subsets and then build models upon those random subsets and then use some sort of ensembling mechanism. And in doing so, you limit the chance that any corrupted data is going to actually influence your final output by that ensembling mechanism, because the corrupted data is then only able to potentially influence a subset of the output models. And if it's only able to influence a subset of the output models, it's unlikely going to be enough to change the ensemble prediction. Pardon me. Now, another advantage of looking at training time attacks is that they're not just useful for thinking about things in terms of robustness, but they also have implications for areas like deliberate unlearning, which is an interesting area of research that's currently really seems to have some interesting applications. So to kind of wrap things up, I guess I just want to take things back to the context of why we care about these kind of models. When we're looking at kind of security conscious systems, if we think about a model's performance in terms of just looking at its headline figures, its accuracy, its loss functions, we can really miss the potential for adversarial examples and the incentives behind people wanting to construct adversarial examples to really, and how important those potentially are in changing the model's behavior. Now, one example which to me is interesting in terms of adversarial examples in the real world is that recently Tesla announced that they're going to remove all radar features from future Tesla cars, and they're only going to perform their automated driving systems using a series of cameras. Now, the problem with cameras is obviously they're very sensitive to visual system issues and the robustness problems that kind of plague visual systems. An example of this is that is this figure in the bottom here, which is an adversarial attack on a stop sign, where a few carefully placed little bits of what could be graffiti, but in this case are just stickers, have been placed on a stop sign, and they're enough to change the classification of the model from thinking this is a stop sign to, I think from memory, this changed it to being a right-hand turn sign, according to the model's perceptions. Now, when we have, so this is an example of both why visual systems, we have to be awfully careful about their application and their kind of the risk of robustness. But also one thing to think about also is that LiDAR and radar systems in terms of automated cars aren't just useful in terms of their performance by themselves, but they're also a system that would theoretically be much harder to construct an adversarial attack towards, or at least it's conceptually much more difficult to me to construct an adversarial attack to radar data as compared to strictly visual data. Obviously, they're not all reporting the same information, but it's something to think about. And so I think really the important kind of note from this presentation, or the thing I hope that people take from this presentation anyway, is that due to the implications on trust and performance of robustness, it's important to both think about the robustness of models and also to think about ways that we can kind of quantify how strong or how confident we are in a model's prediction, not in terms of just the model itself, but in terms of how confident we are, even in the light of potential adversarial examples changing the behavior of that model. And with that, that's it for me. Thank you for your time. And if anybody's got any questions, I'd be happy to kind of answer them. Thanks.
Andrew, I have a question.
Sure.
For students in the audience that might be listening, what do you think are sort of exciting directions sort of in certified robustness for others to work on, like emerging or even just sort of adversarial learning more broadly?
I think in general, I think adversarial, to me, certified robustness is definitely the area of adversarial work that's really interesting, because I think there are definitely always possibilities in developing better attacks and potentially moving away from techniques that are based upon gradient descent or trying to work out stronger techniques. But I think the kind of the attacker defender paradigm, I think, leaves that as being like your work can be a bit niche, but looking at kind of trying to better ways of certifying systems and really providing better guarantees of that no matter what perturbation, that no adversarial perturbations exist within some sort of radius. I think that's particularly useful. I also really think there's a lot of potential for looking at attacks, defenses, and certified defenses to models that move away from just visual data. The entirety of the community so far is really looking at visual data. It's CFAR, ImageNet, MNES. And I think there's a lot of opportunities to look at different kind of structures of models. So it might be like graph models or models of time series data is something I'm personally interested in. I think there's definitely applications there for predictive work. And I think also just kind of thinking about different systems that can be corrupted. Like I think going back to like one of my early slides about kind of the Google Maps attack or attack. Those kind of things where there's clearly an adversarial incentive happening, but there's not any research on what that kind of means in adversarial behavior. That's also potentially another interesting thing. Basically, I think there's lots of really interesting things in this field. So if you have any specific questions, any students, feel free to email me anyway at any time. But yeah.
Thanks.
Hello. Just got one question that might not be that related.
Okay,
when I look at the also noise method and polytope method, it reminds me sort of Bayesian neural networks. Has there been any works done using Bayesian methods in this field?
There haven't been many. I think there's one off the top of my head that's looked at adversarial defenses or adversarial attacks on Bayesian models from memory, but there hasn't been anything on robustness using Bayesian mechanisms, which now you mention it is actually quite surprising. So
yeah, because it reminds me so much of Bayesian methods. Looks exactly the same in a sense.
Yeah, and they kind of are Bayesian methods, but they're just, I guess we're trying to move away from probabilities to expectations, but there's nothing necessarily inherently that would stop you working in Bayesian methods. So no, yes, that might be another really interesting avenue to kind of take these things, I think, or at least to consider these things in context of. If there aren't any other questions, it might be good enough time to wrap things up here. So thank you very much, everybody, for coming. And if you've got any questions, please feel free to send me an email or hit me up on Slack if I'm on Slack rarely, but send me a message. And thanks again.
Thanks, Andrew.
Thank you.
Bye.